Hi, I'm Chris Brown, and this is lecture 2.16b in axiomatic design of manufacturing processes. For the next few minutes, we're going to be talking about a case study in correlation between curvature and fatigue. This is part of some research that was done in collaboration with the École Normale Supérieure in Cachan in France, near Paris. And Margot Velouz was a graduate student who worked in our lab. This is another graduate student who was doing his doctorate on this work, and these are Professors Lartigue and Quinsat are professors there at ENS Cachan. And Steve Cordell, Matt Gleason, and Adam Lemoine are all students here at WPI, undergraduate students who've developed this curvature analysis. It was presented at the second SERP conference on surface integrity, which was held in May of 2014 at Nottingham. So the objective is to support product and process design by finding strong correlations between topographies, which are DPs in product development, and ball-in mills, which are PVs, and steel specimens, and their fatigue limits, which could be an FR. So let's see if we can find the relationships. Actually, in this work, I'd like to point out we did a remarkable job in finding a very strong R-squared correlation coefficient of 0.96. So our approach is here to mill surfaces with different conditions, do fatigue and 4-point bending. Curvatures are calculated from profiles extracted from the measured topographies. Now, this work was done here in the United States. This was done in France. And then these curvatures change with position and with the scale of observation. And it's a kind of multi-scale analysis. And then we examine correlation strengths as a function of scale. So where is the value in surface integrity and metrology? And it's really in being able to find these kinds of correlations to support product and process engineering. So here's an example of this ball-in milled surface. So let's take a look at multi-scale characterizations, slope and curvature. First, we've discussed the height parameters previously, and then we've talked about slope on the surface as being the first spatial derivative, curvature is the second, and this is what we're going to use here. So in this direction, we're doing spatial derivatives, and the derivative, of course, is just a finite approximation because we're dealing with distinct data. You could actually fit a curve to this and use the formula for that curve to do derivatives, and some people do it that way. We prefer to work with the actual data. And this is the way we're doing it in the discrete form. So this method of finding curvature from 3 points comes to us from long ago, and here are the formulas by which you get the curvature. The scale in this case is the distance between the two extreme points. And while anyway, and so we use 3 points, and it fits one curve through those with a constant radius through the curve. So the geometric stress at a stress concentration can be based on curvature, and or 1, which is the same as 1 over the radius. So here is the radius of a notch. And other models have been proposed that use, again, the radius, but some of the height parameters along with it. Here's the material, and here's the material specs. Here's how the ball-in milling was done. So it was done by inclining a ball-in mill, which is spinning and feeding in this direction. And it was done on a 5-axis milling machine, and we got 6 different surfaces and approximately 80 specimens for fatigue testing. Excuse me. So here's the machining conditions, and here's with stress relief. So the red have been stress relieved and the blue have not. They were measured with a 3D steel microstation with a sampling interval of 625 nanometers. And all measurements were cropped to 700 by 700. And then a modal type outlier filter was used to eliminate the spike artifacts from the measurements. And there's two parameters in that. One is the risk, and the other is the number of modes, and that's how we assign those in this case. So when we try to make the correlation with conventional height parameters, and here are the values for the different conventional height parameters as a function of the specimens, we're not seeing a strong correlation. Here's a couple of renderings of the measurement. So you can see when we're using a -3 degree tilt on the surface is, markedly different than it is with the 45 degree tilt. Fatigue tests were done in 4-point bending. As I said, about 80 specimens, and here's here's the fatigue curves and what those look like. So we're coming out here to the fatigue limit and the maximum stresses for the different fatigue limits. So here's the fatigue limits in megapascals, and again the inclination of the ball end mill and whether or not it was stress relieved. So here's a profile. Here's a curvature profile based, on that profile at a scale of 150, and there's one at 500. So at 500, because we're using a 3-point method, we evaluate far less of the curve because we can't evaluate the outside the ends, as our third point is falling outside the end. So here's an example to a comparison of the two surfaces. Here are curvatures versus scale and position. So scale in this direction, curvature in the vertical direction, position across here. And again, as we get to the very large scales, we're able to assess the curvatures only in the small part of the center. Whereas here at the small scales, we're getting all of the ones along the profile. So here is a comparison between the -3 and the 45, both stress relieved. There's transverse and longitudinal loading of the two. Alright, so here's some different things we tried. So Margot was here trying to find correlations between the curvature and the fatigue limit. And so this wasn't too bad, 0.76. I think it's better than anybody else has done. And it's done at a specific scale. Here is another try. We'll take this, the mean plus of the 10 maximum. So that turned out to be a little better. The maximum plus 1 standard deviation, maximum of the mean plus 1 standard deviation didn't seem to do this very well. What worked very well was the maximum of the means and with 2 standard deviations, and that's where we get the very high R-squared coefficient at, again, a particular scale. So here's R-squared as a function of scale using the mean plus 2 standard deviations. So we can see there's a very narrow scale range where we get the highest correlation. It doesn't occur throughout. And so here are the two non-stress relieved, and they lie right on about the same line with the stress relieved. So it's interesting here, in this case anyway, that roughness sort of dominated the fatigue behavior more than stress relieving did. So in summary, scales of measurement influence the analysis of curvatures. We want to make this part of a proposal for a U.S. standard. The curvature at about 0.6 of a millimeter correlates strongly with the fatigue limit for steel machining by ball and milling in this study. This would be the best DP. This is a question that we looked at previously, but can it be a scientific discipline based on a few laws, or is it an experiential discipline? And we note that scientific disciplines are easier to teach. And there were three things that we needed: characterizations of the appropriate scales, characterization of the appropriate geometrical aspects, and then sort of a corollary that the measurements had to contain the appropriate scales. So this the study and the previous one that we looked at on friction shows the importance of selecting the right scale, like we're in an old sort of dial-operated radio, and we're trying to tune in a radio station. If we listen to the whole band at once, it makes no sense. When we sort of tune in and can just take, you know, a small portion of that, then it makes more sense. So in order to understand anything, the bandwidth needs to be appropriately limited, and the tune the central frequency needs to be appropriately placed. All right, three of our usual acknowledgments, and thank you for your attention. So here's a variation on Heron's method showing how it is constant over an interval, and the double spatial derivative is not, so we prefer to go with Heron. But thank you for your attention.